to answer your question, he can. If he denied, that is also okay. Okay, so do not blame him if he is not going to answer your question, because everything is very clear. If you still have a question, you can just make your own assumption. State that assumption very clearly, what assumption I have made, and I can proceed like this. So that will be fine, because I prepared a solution already. Shouldn't be any very difficult problems for you guys. Okay. So he told me that he will try his best to help you, but still he cannot guarantee he will understand everything. Okay. So he will have a solution in his hands, but he will not show the solution during the exam to you. And also 2 questions. You are supposed to finish in 1 hour, but just as we would have done in last time, I give you more than 1.5 hours. So this is a privilege. You can do exam on Friday. He will give you maybe more than 1 hour. It's up to him. I told him to give you some extension. That will be okay. And if you have questions before the exam, you can email me or go to him. Because he took this course before, he did very well. He is supposed to understand everything. Okay. And I'm going to do a review. After this review, you should be more confident about what you do in exam. And basically, after exam 1, we learn 2 things. The first one is so-called structure idealization, skin-stick model, how to do the analysis, stress analysis on the skin-stick model. What is the direct stress in the boom area? What is the shear flow in the skin? This is the first thing we learn. The second thing we learn after exam 1 is the composites. The other one is just a preliminary introduction, because we have another course in this department about composites. So that one is very preliminary. And what is the so-called structure idealization? In realistic aircraft structure, the cross-section of a wing may be like this. You have thin wall, and you also have some stiffener. So this is just like a realistic wing cross-section. YZ. Right? When you apply some loading on this wing structure, some bending loading about the y-axis, bending loading about the z-axis, and also shear force along z direction, shear force along y direction. What is the stress distribution in the wing cross-section? This is a question we are trying to answer by this hand calculation. What is the direct stress? Direct stress means this direction, out of the plane direction. And what is the shear flow in the skin? So direct stress, the majority of the direct stress will be carried by this stiffener. And the shear flow, the shear stress, will be carried by the skin. So that is called structure idealization. We simplify this structure as a skin-stick model. Simplify those stiffener as the boom area. So this is idealized aircraft structure wing. And this is called boom area. And this is a skin. So the formula for us to calculate the direct stress in boom areas and the shear flow in the skin is sigma x and the q, right? But before you can use that formula, you need to calculate the sectional probability, right? The area moment of inertia. This one, if this is a y, this is z, this is the center of gravity. So the first step is to identify where is the center of gravity. if the cross-section is symmetry, about every axis should be in the just middle point. But here, maybe it's not that symmetry. You need to identify where is the center of gravity first. After you identify that, you can use this to calculate the area of moment of inertia. Second one is AY. Third one is so this is a moment of inertia in that coordinate system. This coordinate, the origin of this coordinate is at the center of gravity of the cross section. And YIZI. AI is the area of each boom. Okay, each boom area will have a value. Boom area value. Okay, A. You have n boom areas. You have n terms. And each boom area will have a coordinate along y direction, along z direction. So this is how we calculate the area of moment of inertia of this cross section. And then we have this, the direct stress, sigma xi. That means direct stress along x direction, this direction. I means ith boom area. Okay? You have a formula for this. This IYY and Y and Z, sorry. This is a formula that I'm going to use to calculate the direct stress on the boom area. IYY, IYZ, and IZZ are calculated through these two formulas, and MZ and MY are the moment you applied about y-axis and z-axis. It's external loading, bending moment. So a special case is if this cross-section is symmetry, that means IYZ will be 0. If you only apply the moment about y-axis, this is yes. YI, ZI. Thank you. Yeah, because each boom area will have a different direct stress. It's a function of YI, I have that in my notes. So a special case is when you only apply a moment about the y-axis, then mz will be 0. This is what we did in homework, right? Most likely we are dealing with symmetric cross-section and only apply one bending moment, so it can be simplified. My, zi, iyy. This is a direct stress in the ith boom area. And if you want to figure out the force, F, X, I, this is a force acting on the ith boom area along x direction, will be sigma xi times ai. Right? Force times area, you get force. Stress times area, you get force. So this is a formula for the stress and the force. And next thing we learned is what is shear flow. This is a direct stress. Okay? Direct stress is carried by the boom area. Shear flow is carried by the steam. So about shear flow, we start with the simple case. Shear flow in open section beam. Open section beam is always easier than closed section because it's determinate. Each equation will only have one unknown, and you can determine the shear flow very easily. But for closed section, you will have indeterminate equations. You will need more equations to determine shear flow. So open section, what I mean is like this. This is a typical idealized open section wing cross section. And boom area is 1, 2, 3, 4, 5, 6. This is a coordinate Z, and if loading along this direction is Vy, loading along this direction is Vz. And this is a typical open section beam. And what is the shear flow in each scheme? We need to figure out that. The formula that we can use is this one. QI, the general formula. So this is a general formula that we can use to calculate the shear flow in each scheme. But actually this formula is for the ice boom area. The term on the left is one of the shear flow associated with the ice boom. Okay, how many booms, how many schemes are connected with this boom area? You will have how many terms on the left? On the right, you only have one terms. You only have two terms. Okay, the first term is this one. The second term is this one. And IYY, IYZ, and IZZ are calculated. Is the same as what we have done for this one. IYY, IZZ, and IYZ is the same. The formula for this area moment inertia is the same. And Vy and Vz are the loading shear force applied along y direction and z direction. And AR, YR, ZR, we should say this is R's boom area. We're dealing with R's boom area, so this equation is for the R's boom. Okay. This one on the left is one of the shear flow associated with this boom. Okay? And a special case for this is if Vy equal to 0, Iyz equal to 0, Vz is not 0. This means if the cross-section is symmetric, and the equation can be reduced V, Z, Iyy, AR, ZR. This is a reduced equation for the symmetric cross-section. So I would like to briefly introduce the structure. I put it here. Maybe just use this one. So this is the equation we have, right? So let's look at the forced boom area. This is the forced boom. And on the left, as I said, on the left is one of the shear flow associated with the earth boom. Right now we are dealing with the first boom. So one of the shear flow associated with the first boom, only one, right? Because only one scheme is connected with this boom. Now you only have Q12. This is the term on the left. Because for the first boom, you only have one shear flow. And the equation will be on the left, will be Q12. Why it is Q12? Because I predefine the shear flow going outwards is positive. So Q12 means shear flow is flowing from the boom area 1 to boom area 2. So this is positive. This is the term on the left. I'm using this equation. So on the right, VZ is given, IYY is calculated from the beginning, and ARZR, you are dealing with the first boom, so it becomes A1, Z1. Okay? A1 will be the area of the first boom. Z1 will be the coordinate of the first boom along Z direction. Okay? So this is the first equation. And why the open section boom? Question? Why the open section boom is easier? Because you have only one unknown and one equation. Right? You have a free end there. Right? The first boom, only one shear flow is there. You have one equation. This is the shear flow you want to calculate it. So this is why open section is easier. And you can do the third boom, Q32, right? You're assuming shear flow is flowing from boom area 3 to boom area 2. And the equation you will have on the left, Q32. And on the right, VZ, IYY, A3Z3, because you're dealing with the third boom area. So ARZR becomes A3Z3. When you figure out this, and then you can come to the second boom. Because for the second boom area, you have 3 shear flows. You only have 1 equation. You have to figure out the 2 shear flow first, and then you figure out the other one. Because for this one, going to use another paper. So for that one, the shear flow will be like this. This is 2. So shear flow Q12. You already saw from the first boom area, and Q32. You solve that from the second boom area, from the third boom area, and then you have another one, Q25. This is one of the shear flows associated with the second boom area. And then on the left of that equation, you have Q21, positive, going outwards. Q32, negative, is going inwards. And Q12 is also negative, going inwards. On the right, VZ, IYY, A2Z2, because you are dealing with the second boom area. Because we already calculated this one and this one from the first equation and second equation, and then one equation, one unknown, right? We can figure out the shear flow from boom area 2 to boom area 5. You cannot, in this equation, you are using the same index, Q32. You are not using Q23, because what you calculated is 32. If you insist, if you say, I want to use Q23, you have to switch, you have to flip the sign, because we predefine the direction of the shear flow. Okay? From 2 to 3 is the direction, that one is positive, then from 3 to 2 must be negative. So be careful about the sign of the shear flow. If you define a sign, do not change the sign during the calculation. You will mess up. Okay? So this is how we calculate the shear flow in open section beam. Open section beam is easier, as I said, because you have free end and the equations and unknowns are the same, so you can do that one by one and figure out all of them. And the second question we answered is, what is the shear center of the open section? Again, we use this one as an example. This is the open section. So if you already calculated what is the shear flow from according to what I have introduced for open section, you can calculate what of the shear flow in each scheme, and then you plot all of the shear flow on that scheme. This is all of the shear flow. Suppose this is your calculated shear flow on this open section beam, and then the question is, well, I'm supposed to apply my VZ on this structure such that there is no any twist. This is the definition of shear center. VZ, because when you are trying to calculate shear flow, you do not define what is the location of VZ. It can be anywhere, right? It's along Z direction, but you do not tell from the previous calculation, you do not define where is the location of VZ. So this is the second question we're trying to answer. Well, I'm supposed to put my VZ such that this VZ will not induce any twist of this cross section. This is the definition of the shear center. Because if you apply your VZ not on the shear center, the cross section not only be the beam, it's not going to be bended only, it's also going to be twisted. Okay? So shear center is a very special point. When you apply the force along that point, there is no twist. So how to calculate what is Kc, the location of Kc? According to that definition, there's no twist, means the moment should be balanced. I take the 7th point. There's a point there, 7th spoon area. You can take the moment balance about any point, okay, for your convenience. In the exam, I already assigned which point you should take the moment balance, such that everybody is using the same moment balance equation. Okay. So for this one, I'm taking the moment balance about the 7th spoon area. So how to do that? The clockwise direction is positive, and counterclockwise direction is positive. Clockwise is negative. So this is, we calculate that term by term, and then we calculate the external force contribution first. VZ times Kc is counterclockwise, about 0.7, right? Force times this much is counterclockwise, so it's positive. VZ Kc. This is a moment contribution from the external force, and then shear flow. Shear flow is a force. Shear flow is a force, but the unit of shear flow is force per length. Okay, that is how we understand shear flow. Shear flow is a force, but it's force per length. And if you take the contribution from the to the moment from the shear flow, what will the shear flow going through 0.7 shouldn't be contributing anything, because that force is going through that point. So you only have this one, this one, this one, this one, not this one. So 1, 2, 3, 4. You only have 4 terms, 4 shear flows. This one, this one, this one, and this one. These 4 shear flows are not going through 0.7. They should be contributing to the moment about 0.7. So we do that one by one. The first one, Q12, right? Q12 is along this direction, counterclockwise. So it should be positive. Should be positive. And what is the formula for that? Moment calculation is this. Actually, I derived this in my lecture. Why this shear flow times area times 2, you get the moment. I derived this while doing the lecture. So this is the moment contribution to 0.7 from the shear flow 1-2. You see Q12 is here and times the area. So what is the meaning of A127? 127 is this area. Basically, 127 means you connect 0.1, 0.2, and 0.7. You form a triangle. And then you calculate the area of that triangle. You get A127. And Q12 is calculated in the first step. So this is the first term. Second term is a moment contribution from Q32. It is clockwise. So it's Q32, A327. So 327. No matter it is a straight line or curved, what if this skin 27 is curved like this? No matter it is curved or straight, it just connects 3 points. You will form an area. Calculate the area. And then times shear flow times 2. You got the moment contribution. Okay, this is what you did in homework. Just calculate that area. So 327 means you connect 0.3, 0.2, and 0.7. You will form an area. And calculate that area. Times 2 times the shear flow. And this is the second term. Third term is Q34. A347. Also negative because it's clockwise. And then 65 is also negative. 65 A657 equal to 0. 4 terms from the shear flow contribution. The total moment balance about 0.7. The first term is from the external loading, and the other 4 terms are from the shear flow 1, 2, 3, 4. Okay? And what is A657? It's area like this. Connect 0.5, 0.6, and 0.7. This area is A657. So in exam, in homework, we're going to do in homework we did this already. In exam, I'm going to ask you to calculate. I'm not going to give you one of the area. You have to figure out some area by yourself. Okay? Do that carefully. Do not make a mistake, and then you can figure out what is the moment balance equation, and then calculate what is Kc. The only unknown in this equation is Kc, right? Because Vz, all of the terms in Q will contain Vz. Vz will be cancelled. Okay? Vz will be cancelled. And area you can calculate it one by one. And shear flow you already calculated. So there is only one angle from this equation. That is Kc. From this equation you can calculate what is the location of the shear center. So this is a definition of the shear center open section. And then we come to closed section. So shear flow in closed section beam. The equation we're going to use for open section and closed section are the same, but we have two additional equations that we can solve because closed section is indeterminate. We need more equations. So the first equation about shear flow will be the same, but we need more equations. A typical closed section is like this. This is also one example I did in class. There's no free end. Everywhere is connected with skin. All of the boom areas are connected with skin. And suppose this is Vz, this is y direction, this is z direction. For shear flow, as I said, equation will be the same. The first equation, the equation is this one: Iyy Vy minus Iyz Vz Er Yr minus
Are you sure you're not the viewer?
I'm one.
during the exam. If you know what is the equation you are supposed to use, just write down the equation. You will get some points. Do not leave the blank. That's not wise because calculation is very easy to make a mistake in calculation, right? But you're supposed to know which equation you're supposed to use. Moment balance, shear flow. If you know which equation you're trying to use, write down your equation very clearly. Otherwise, I will not know your calculation is wrong or you are using wrong equation. Okay, this is totally different. If your calculation is wrong, that is acceptable. But if you do not know which equation I use, that's unacceptable. You definitely will lose lots of points. So you have to tell me, you know which equation I'm trying to use. Okay, and no matter it's shear flow, or moment balance, or direct stress. The first step, write down your equation you're trying to use. Okay. This is the shear flow for closed section. It's the same. You see, this equation is the same. And if we do that
like there's probably an app for the
boom area one by one, you figure out why we need more equations. Not only this one. The first boom area will be Q12, Q31. The second one will be Q12, Q23. And third one, Q23, Q34. Fourth one, Q34, Q41. Look at these 4 boom areas. You only have one equation for shear flow, right? That equation is valid for each boom. So when you take the first boom, when you do the first boom, you have one equation, 2 unknowns, this one, this one. When you use that equation for the second boom, you have 2 unknowns, this one, that one equation. No matter which boom area you start with, you always have 2 unknowns, but only one equation. This gives you an indeterminate problem, right? That means you need one more equation to determine the shear flow. So that equation, first we can reduce this one with if Vy is 0, Vz is not 0, Iyz is 0, the shear flow is again reduced to Vz, Iyy, Ar, Zr. So this is a reduced equation if this cross-section is symmetry. Again, no matter which boom area you start with, you use this equation, you have 2 unknowns. You have 2 unknowns, 1 equation. So one more equation that we can use if you only have one cell. This index, this I, stands for the index of the cell. For this problem, you only have one cell. Cell means closed cell, you have multiple cell, you have one cell. This is single cell cross section. Okay? So this I only here equals to 1. So this equation means if you apply your shear force, this cross section on the shear center, suppose you are applying your shear force on the shear center, there will be no any twist. Twist means d theta dx will be 0. D theta dx is a twist angle. Okay? There's a formula for d theta dx is, what is d theta dx? So d theta dx is equal to 2a qds dt. This is a definition. You should have not dt, gt, I'm sorry. G is the shear modulus, T is the thickness. So Q is the shear flow along the skin. ds is the hoof direction. You have a closed section, right? ds is along the hoof direction. So for a rectangular shape, just convert that hoof direction integration to a summation for edges. Okay? For circular shape, you need to do integration. So how to do that? How to convert this to a, this is a 1, 2, 3, 4. This is an example we're trying to do, right? 4 boom areas and some skin, 1, 2, 3, 4. So 4 skins. I need to convert this integration to a summation because this ds is this. It's along the hoof direction. So there will be 2a. A is the area of the whole cell. Okay? 1, 2, 3, 4. The whole cell will give you an area. So 2a will be there, and that integration you can convert to a summation. 1, 2, L, 1, 2, G, 1, 2, T, 1, 2. I'm dealing with this edge because you are doing hoof direction from here to here, right? So I'm going to deal with the first edge first, 1, 2. Q1, 2 is a shear flow. This term, Q, shear flow from 1 to 2. ds, do the hoof direction from 1 to 2, you get a total length from 1 to 2. Right? L1, 2. is the total length from point 1 to point 2. Right? G12, T12 is the shear modulus of that skin and thickness of that skin. Okay? Because in your homework you did something like this. The skin have different, the thickness of the skin are non-uniform. Means you have one thickness for this one, you have another thickness for this one, another thickness for this one. So you have to do that term by term. And also, it's very possible that you are going to have different shear modulus for different skins. So that is G12, is the shear modulus of that skin. So 4 terms until Q41, L41, G41, T41 equal to 0. I skipped the 2 terms. One is this one, another one is this one. So this is the last segment. Okay, you have 4 segments in total. You will have 4 terms to convert that integration to a summation. And then from this, A is the total area, GT are given. Thickness and modulus you are given. Shear flow is the shear flow you are trying to figure out. And L is the length, arc length. If it is a line, just you have a straight line. It's very easy to calculate length. For this one, you have to calculate it, the length from point 2 to point 3 sometimes. Right? So you have everything except the shear flow in this equation. You have Q12 is to be solved, Q23 is to be solved, Q34, and Q41. In this equation, you have 4 terms, 4 unknowns. But previously you have 4 equations already. We are using this equation, VZ, IYY, AR, ZR. From this equation, you use this equation boom area by boom area. You have 4 equations in total. And then you have one more equation, right? All right, this 1, 2, 3, 4. 1, 2, 3, 4, yeah. From if you use this equation in boom area 1 by 1, it's not solvable because this equation, each equation will have 2 unknowns. And for this one, when you use this additional equation, what's wrong with this? When you are using the additional equation, you can solve all of the shear flow. Okay, we did this in homework. I didn't go through the details. If you want to figure out what is the details, you just go back to check your homework. We did one problem like this. And this is how we calculate shear flow in closed section. And what is the shear center of the closed section? This one has no difference with the open section. If you figure out all of the shear flow in this closed section, 1, 2, 3, 4, and if you already calculated all of the shear flow, and this is VZ, and if this is the KC you want to calculate, you are trying to figure out what is the location of the shear center. Okay, I'm trying to figure out that. Again, you can do the moment balance. This is the same as what we have done in open section B. After you figure out the shear flow, everything is the same as the previous open section. Do the moment balance, figure out the shear center, location of shear center. You can take the moment balance about any point. I'm taking the moment balance about this point, so about this point, VZ times KC is negative, right? It's clockwise. Taking moment balance about point 1, VZ will be negative. The moment from the VZ will be negative, clockwise direction. So shear flow from 1 to 2 is flowing through point 1, not contributing. Shear flow from point 4 to 7, from 4 to 1 is not contributing, it's going through point 1. Only this one and this one is contributing. So that one, 2, 3 is positive, Q23, A231, and 234, A341 equal to 0. Okay? The fourth term is a moment from the external force. Okay? And the second term and third term is the shear flow contribution to the moment, about 0.1, 2, 3, and 3, 4. And what is A231? This one is the area you connect 3 points, 1, 2, 3. 1, 2, 3. You are going to form an area. It's this. It's not that triangle from 1, 2, 3. It's not a triangle area. 1, 2, 3. It's a total area. Okay? So A231 is this much, not just that triangle. Some students made a mistake in homework. When they are trying to calculate 1, 2, 3, 1, they only calculate this area. That is not correct. Okay? Because this should be the total area included, connected by these 3 points. If I'm curved line, you should include that. And 3, 4, 1 is that triangle. 3, 4, 1 is this one. Okay? So you calculate this, you calculate this, and you calculate what is C. So this is how we calculate the shear center of the closed section. This is the same, actually, as what we have done for open section. And one more thing we learned is if we have multiple cells, shear flow in multi-cell wing structure. So that means something like this. One, 2, 3, 4, 5, 6. If this is the wing cross section, this is most likely this will be the wing cross section, right? In reality, this is the most possible, right? So you will have 2 closed cells. Each of them is a closed section, and you need one more equation. That equation is, this is VZ. That equation is these 2 cells has to be having the same twist angle. D theta dx2. This is the additional equation we need because you have 2 cells, or even 3 or 4 cells in your cross section, and then you have pattern loading, shear force or bending. These 2 cells has to be deformed together. Otherwise, the structure will be falling apart. So that means twist angle has to be the same, continuity, right? Otherwise, these 2 cells will not be together. So this is why you have this equation. And from this, according to the definition of the twist angle, you write QS GT. This should be first cell, and A2 QDS GT second cell. So I just, according to the definition of twist angle, I write the equation for d theta dx. For different cells, you will have different area. A1, A2 is the areas, is the area of these 2 different cells. And then here is the shear flow. For example, for the first cell, you have shear flow here, here, and here. I can elaborate the term on the left. Okay. I convert that to a summation. It will be Q 5,4 and length 5,4, G 5,4, P 5,4. I'm dealing with the shear flow from point 5 to point 4. Okay? And second term is from point 4 to point 3. Q 4,3, 4,3, G 4,3, P
Are we
4
doing any what?
Last term is from 23 to 25.
Fake injuries.
2, 3, 3, 5.
SABC, that was it.
P 3, 5. P 3, 5. And you can follow the same procedure to write down what is on the right. Okay, so this is an additional equation we can use if we have multiple cells, because this will give you another relation between the shear flows. You have some shear flow on the left, this one, and this one, and you will have some shear flow on the right. They should be related. This relation will guarantee these two cells will be twisted together. Okay, so this is why we have one additional equation for this. Okay, this is one of the things we have learned in steam stick model: direct stress, shear flow, and shear center. Shear flow in open section, shear center of open section, shear flow in closed section, shear center in closed section, and then shear flow in multiple cells. Okay, this is what we learned in steam stick model, idealized structure idealization. And this kind of calculation is not accurate. I can assure you, this is just to give you a sense. Which part have the highest shear flow, which part has the lowest shear flow. It's not accurate. It's approximation. You can see that this, because you just simply assume this stiffener as the bone area. That's definitely is not accurate. Okay, so you will compare. You need to compare your hand calculation with your answers. And then maybe I need 5 more minutes to review about composites. Okay, so that's very easy because we didn't go very deep about the composites topic. You are allowed to have 2 pages of formula sheet. Okay, just write down all of the equations you feel you're feeling that it's going to be useful for your exam. Okay, 2 pages of double-sided, so you can write down many things. Do not about composites. You have many equations to write down. Okay, so the first terminology we learned is called micromechanics. Micromechanics of analysis for composites. The definition of micromechanics means fiber and matrix, or filament and matrix, are considered separately. Okay? This is the definition of micromechanics. So the first equation we learned in micromechanics is EL equals to EF VF plus EM times VM. If this is a composite, and this is a filament, and this is L direction, this is T direction. L means longitudinal, T means transverse. Okay, EL means the modulus of this composite along the longitudinal direction. Okay, because you are trying to combine a filament and a matrix to form a composite. So the modulus has to be formed from the modulus of the filament and composite. So this is a modulus of the filament, this is a modulus of the matrix. And this is a volume ratio of the filament, and this is a volume ratio of the matrix. Okay? You did this in homework. It's very easy. Just calculate what is the volume ratio and plug in. You get the modulus of the composites. And another modulus is the transverse modulus. It's EM, EF times VM, EF plus VF, EM. This is a modulus along this transverse direction. You combine filaments and matrix. The modulus along the longitudinal direction and the transverse direction will be different. So this one is for longitudinal direction, this one is for transverse direction. And also Poisson's ratio will be different. So the first one is so-called major Poisson's ratio, mu LT. Okay? Mu LT is equal to mu F VF plus mu M VM. This is major Poisson's ratio. Okay? The physical meaning of major Poisson's ratio is the decrease of the transverse direction divided by the elongation of longitudinal direction. Okay? The physical meaning of Poisson's ratio: you apply a loading on some direction, that direction will be elongated, but the other direction will be shrink, right? The difference of the transverse direction divided by the longitudinal direction elongation, you get the Poisson's ratio, major Poisson's ratio. And another one is minor Poisson's ratio, UTL. This one is ET, EL, UF, VF plus UM, VM. So UF and MUM is the Poisson's ratio of the filament and the matrix. And VF and VM are the volume fraction, the volume fraction of the filament and matrix. So this is modulus and Poisson's ratio. Another one is shear modulus. Shear modulus GLT equal to GM, GF, VM, GF plus VF, GM. This is the shear modulus. Okay, this is micromechanics. And then we learn something is called macromechanics. In this approach, we consider the filaments and the matrix together. Okay? We're trying to form what is the relation between the stress and strain in the composite component and the composite. If you apply some loading, what is the deformation? What is the deformation of this composite? Basically, the question is trying to answer. If you apply loading on composites, what is the elongation? What is the strain? So the first thing we learn is spatially isotropic applies. This means the filament, this is the filament, is along the x and y direction. If this is x, this is y. Okay? The filament is along the stress direction because you are going to apply sigma x, sigma y along x and y direction. The second one is so-called generally isotropic. In these composites, the filament is inclined along x and y direction. So you put your filament like this way. You have a theta angle here. So if this is x, this is y. This is L, this is T. This is L, this is T. So especially isotropic applies, L and T are along x and y direction. And in generally isotropic applies, this LT is not along x direction anymore. When you look at the filament, this is L direction, right? And this is T direction now. Right? In generally isotropic applies, L and T are not along x direction and y direction anymore. So this is the difference. And we derived something for especially isotropic applies first, and then we do the stress transformation. So the basic equation for especially isotropic applies is this one. You are going to need some equation I wrote here. Okay? Mu LT, mu TL, mu TL, EL, 1 minus mu LT, mu TL, 0. This one is mu LT, ET, 1 minus mu LT, mu TL. And this one is ET, 1 minus mu LT, mu TL, 0, 0, 0, GLT. And this one is epsilon L, epsilon T, gamma LT. This is the most fundamental equations we're going to use. This is the equation to relate the stress and the strain for especially isotropic plies. And then we do some transformation. And then we get the stress and strain relation in generally isotropic plies. So this one is most fundamental, right? The relation between the stress and the strain for the especially isotropic plies. Sigma L, sigma T, and tau LT, epsilon L, epsilon T, and gamma LT. And then from this equation, we use stress transformation equation to get sigma L, sigma T, tau LT. This is m n 2m n n square m square 2m n minus m n m n m square minus n square. Sigma x, sigma y, tau xy. This is a stress transformation equation. We are going to transform the stress along the longitudinal direction and the transverse direction to the stress along x direction and y direction. On the right is the stress components in xy coordinate. On the left is the stress components in LT coordinate. So they are related. Mn is related with the inclined angle. Okay? M equals to cosine theta, N equals to sine theta. And we have one more equation, and then it will be dismissed. Okay? So T gamma LT equals to M N square M square Mn 2Mn 2Mn. So this is a transformation equation between the strain, right? Because the transformation between strain is different from the transformation between stress. So that is why you have one more equation like this. Basically, I wrote down all of the equations you're going to need in exams. You can guess which equation you're going to need. I only wrote down 3 equations. So this is what I'm going to have the exam 2. Any questions about this? I prepared the solution already. You should be able to finish in maybe 1 hour and 20 minutes. Should be fine. Some students can finish within 1 hour, I believe. And Chris, we are trying to help you. And before the exam, if you have a question, you can email me. Okay?
I have this, it automatically.
I just like need to listen to it.
Yeah. I have most of the lectures.
I turned it on. I mean, he's going to write down a website, so worst comes worst, to do it Monday, but I have to get going.
That is just a definition.
It's here. Oh, dear Lord. Okay, thank you very much. I'm going to cancel that. That's just super slow. Yeah.
Never mind.
All right, thank you.
What's that? This is the work that I did over the summer. I forgot I had these videos on here.
Someone get shot?
No, we train police officers how to respond to medical emergencies. So this is
Are
a
those
training.
real wounds?
No, that's moulage that we put on them.
Huh.
This is streaming from my computer at home, so it's not the best quality.
So you're training them?
Oh yeah.